Okay, I'm going to try to make a point here that you guys, if you want, can let me know was pointless because I might get a little carried away. Um, but you've heard me say a few times that a common goal in math is to be able to compute solutions, but not just compute solutions. We need to be able to compute solutions quickly, which is a relative term because you know quickly to some people might be 30 seconds if you're an impatient student, or if you can find a solution in 3 days, that might be quickly to somebody doing some pretty important research. So, but you got to be able to find it at some point when you're alive, or else it doesn't really matter that it's a solution. You can, a lot of times math people will like to say, well, a solution exists and that's all we need to know. And that is helpful to know that a solution exists because then you can know that it's good to spend effort finding it, but there has to be an efficient way of computing things. So, and here's where I'm going to go with this to try to illustrate it. We have some idea of what a stock is, and I think I've mentioned stocks a few times already. And you have, you might see these graphs on CNN or something like that where you have time and I guess the stock price, and it has this very uh, typical kind of random motion, right? So, um, one day the stock price for Apple might be $39 a share, and then the next day it might be $39.50 for a share. It's not going to jump up and down from 39 to 150 or anything like that. It's not that volatile typically. Um, so So that's kind of what we understand a stock price to be. It's that we think we might imagine this picture, and we think of a company like Apple, and maybe we can make money if we know what we're doing. But nobody really knows how to predict this stuff. People try to know, but it's very complicated because you're dealing with companies and people and economics, and those are just really unpredictable. But there's a lot of attempts. Now, there's something else about stocks called options. A stock option is a contract that is made between a company and an individual, or maybe between two companies. But it's a contract saying that I can purchase the stock at a certain price in the future. I don't know why this is even in existence, but it is out there and it's used all the time. And people, again, just like investing in stocks, will often try to use this as a way to make money. I don't know who thought of it or why it was thought of, but it's extremely um, important and relevant in economics. So, anyways, it's basically a contract saying I think that the price of Apple will be $45 in November of 2015. If you're that confident, maybe you've done a lot of research, you think, oh, they hired a new CEO or something like that, and you think it's going to go up, and it's going to be at least $45. And if I purchase a contract now to buy it for $45, or I'm sorry, if you think it's going to go up and you purchase a contract now to buy it for cheaper than that, then you make a profit when you sell the contract back. I hope I said that right. So that's the idea behind an option. It's that type of thing. So what if I had an equation that could tell me the price that an option will be in the future? Wouldn't that be something? Well, we don't, but we like to think we do, and that's called the Black-Scholes equation. And it's this really I don't even understand it. And I'm making a point here, so just try to stay with me. But this is what it looks like. I'm just copying this down off of Wikipedia. Um, it's called a partial differential equation, and I think I've seen it just a few times, and I might have even solved it once while I was in grad school. But um, Yeah, that's what it is. Okay, and it says that if you know the what this V represents the volatility, and I don't even remember what the others symbols represent, but there's a lot of stuff going on in there. Okay, this equation. The point is that um, it does somewhat model what's going on, and the nice thing is that it's not insanely difficult to solve. It's complicated, and you need to know a lot of math um, before you can really study it. But they say it's the best equation out there, mainly because it kind of models it, and it's okay. It's not too difficult to solve. And a lot of times, what they'll do is they'll try to approximate solutions to this using linear algebra and matrices, because this to solve it like solving for x is very very difficult, especially if you want to make a more realistic model. Like if you want to build off this and make a more realistic model using the Black-Scholes equation, it can become very difficult. So what they'll do is they'll use computers, and they'll do a trick, and they'll say they'll discretize their domain, and basically approximate solutions by coming up with systems of equations that all have to be true at all these different points. And so you'll get a huge matrix, maybe A11 all the way to A11, 1,000 or something, or 10,000. And you got this 1,000 by 1,000 matrix that you need to find solutions for. And you have 1, 2, and I don't know, pi, and all this other stuff. And you need to find the inverse of this matrix, or find the determinant of it, maybe for some reason. So this is relevant in financial math. Another place that it would be relevant, that they'll do this same process, that I hope is not is I hope I'm giving you a good understanding of what they're doing, is in engineering. There's something called the Navier-Stokes equation, which is an equation that tries to describe how fluids flow. So if I have a pipe, and I have some fluid in there, I want an equation, and it's another partial differential equation that's even uglier than that, if you can imagine. And they'll do that same type of trick where, okay, I can't actually, and that there is no solution to that equation, for sure. But what they'll do is they'll do these tricks, and eventually it'll come down to solving a matrix where you can say, okay, I can't find an exact solution, but I can get close. And so a big field of study is how quickly can I find the determinant or find the inverse of a huge matrix, you see? And then you can make sure you are able to build your airfoil or your wing better. A fluid doesn't just mean water, it could mean air as well. It's just so it's an important part of engineering and finance and things like that, is solving large matrices. But just because I can set up the matrix and I can set up the problem, if I can't solve it, then what good is it that I can set up? I know there's a solution if I have a huge matrix of 1,000 by 1,000 or a million by a million, um, but if I can't find it, it's of no use. So that's the point, is that that's a huge field of research, is trying to find, how efficiently can I compute solutions to these things. Anyways, okay. So similarly, that's what this section is about. Okay, we know how to compute the determinant of a 2 by 2 or a 3 by 3, and if we wanted, we could do a 4 by 4, even though it might take 2 pages. Um, but it's not useful if it takes forever, right? We know that determinant is important, but it's not useful if it takes forever to compute, I should say. So that's what this section is about. There's a few different theorems and properties, and that's what a lot of mathematicians or applied mathematicians might do, is they'll say, okay, we know we can find solutions, we know this thing's important, now let me find a faster way to do it. And that's a huge thing, and it's very, very important to do that. So that's what this section does with determinants, is let's use some properties to maybe find a quicker way to compute it, rather than doing all those cofactors, right? So one of those properties is multiplying a row by a constant. One of the properties um, that you can use to see, all right, how does a determinant change when I multiply a row by a constant? I'm sorry, I'm saying too many things at once. What you can do is you can do row operations on a matrix that we've already learned how to do, and you can simplify it down, and then realize that these row operations change the determinant only by a little bit. And then, if one of my row operations is multiplying a row by a constant, how does that change a determinant? Once I know that, I can use this trick to find the determinant faster. There we go. All right. So, given a matrix A, let's just use the general form A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay? There it is. So if I multiply this by some constant k, okay, let's call the determinant of A would typically be some number alpha. Well, the determinant of A, this new A, which I should call it A star maybe, the determinant of A star just becomes k times the determinant of A, right? Maybe K star, or I'm sorry, A star, maybe A star was easier to find the determinant of. So all I got to do now that if I want to find the determinant of A is I just divide both sides by K, right? And I got to do an example to show you, but that's really all there is to it. So let's say I have 6, 1, 3, -2, 7, -2, 4, 5, and 0. Right? This is example 1 on page 516. All right? So I want to compute the determinant of this, but I realize that maybe I can make my life a little bit easier by factoring out a 2 out of the first column. You can actually factor out of a whole row or a whole column. So here in this example, they factor out of the first column. So if I factor out a 2, then this becomes 2 times 6, -1, 4, 1, 7, 5, 3, 5, 3, -2, and 0. Okay? Remember, those vertical lines don't just mean a matrix anymore. That when they're just drawn like that, it means the determinant of the matrix. So these little brackets, that means a matrix. So if I write 2, 3, 4, 5, that's just a matrix. But once they become just vertical, that's another way of saying determinant of. Okay, it's in the book. So that's what happens here. The multiplying a row or a column by a constant changes the determinant by whatever that number is. So I can factor out now the 2 out of there, and I'm dealing with smaller numbers. This should be a 3. I'm sorry. 3, -1, and 2. Okay, pay attention to what I'm doing. So there you go. Another thing is if you interchange rows or columns, and this can be very helpful. So let's say I have something like I want to find the determinant of 1, 4, 7, 0, 1, 0, and 5, 6, 2. Well, this determinant is equal to this determinant 0, 1, 0, 1, 4, 7, 5, 6, 2. What did I do? I did a row operation, right? I switched the first 2 rows. And why did I do that? I did that because, remember, with cofactors, the determinant, I'm used to finding the determinant with cofactors, but these things are 0. So 0 times anything is 0. So really all I have to worry about is doing this middle column here. So 1 times the determinant of this submatrix. But I have to keep in mind that when I switch rows, I put a negative in front. That's the property. So interchanging rows or columns means I put a negative in front if I do it once. If I do it twice, then I put another negative and it just goes back to normal. So usually you would only interchange one row and you just have to multiply by a negative. So yeah, so now we can compute the determinant of this matrix. So let me just finish this example up. That'll be my example. It'll be negative. So this is 0 times whatever that cofactor is, right? Minus 1 times the determinant 1, 7, 5, and 2, plus 0 times whatever this cofactor is, which we don't really care because it's going to be 0. So we're just taking the advantage of the fact that there's zeros and using this property of determinants to make life easier. Okay, so 1, 2, 5, 7, I should have already done it. It's going to be 2 minus 35 is going to be negative 33. Okay? But with a negative in front. So now I distribute the negative and this becomes positive 33. So there we go. Oh, no. Sorry. Okay, so this is negative 33. Point is that when you switch two rows, you put a negative in front. Okay, so that's that property. What if I have a row of, or a column of zeros? So let's say I have a 3 by 3, and I have 0, 0, 0, A11, A12, A13, A31, A32, A33. Well, now that we know that we can switch rows, this will just be negative of this, and this is originally my A11, A12, A13, A31, A32, A33, right? But look, now these are going to multiply all my cofactors. This whole thing is going to be 0. So this is an example of what's called a singular matrix. This matrix, whatever it's going to look like, whatever numbers I put in for these A's, will not have an inverse. It's a square matrix, but it's not going to have an inverse. Or you could say that well, let's just leave it at that. It doesn't have an inverse. So, example. They do 3, -2, 5, 0, 0, 0, -1, 4, and 9. Okay? So again, we'll just switch 0, 0, 0, 3, -2, 5, -1, 4, and 9. There's a negative in front because we switched the two rows. But now, let me do the whole cofactor thing. 0 times the determinant of -2, 5, 4, and 9 minus 0 times the determinant of 3, -1, 5, and 9 plus 0 times the determinant of 3, -1, -2, and 4. But look, I got 0, 0, and 0. This is all 0. Right? So, you know, I might ask you, if I ask you, please show why the determinant of this is 0, then I want you to do these steps. But if I just say find the determinant of this, and I don't say show steps, and you know I do a lot of multiple choice, boom, now you have a very efficient way of just saying it's 0. Okay. Adding rows or columns. This is, if you remember, this is row operation 2. So row operation number 2. So if I add together two rows or columns, that um, actually doesn't change the determinant. So that's a very nice feature because this is the most useful row operation that we have. So if I take A11, A12, A21, A22, that's the same as this determinant is equal to, I don't know, let me not do that. Example. Let's say 2, 4, 5, and 3. Okay? So let's say I just add together, let me multiply the first row by 2 and add it to row 2. Okay, that becomes 4 plus 5 is 9, and then 8 plus 3 is 11, 2 and 4. These both have the same determinant. Let's go ahead and compute it just to prove it. So 2 times 3, the determinant of this is going to be 6 minus 5 times 4 is 20. 6 minus 20 is negative 14. Well, the determinant of this is going to be 22 minus 36, which is negative 14. You see? So we did row operation 2 and it didn't change the determinant. And that's very useful because maybe we can simplify it down to maybe we get a bunch of zeros everywhere and a bunch of stuff cancels, and then our determinant's really easy to compute. So let's see. What do you think happens if you have equal rows or columns? So let's say I have a 3 by 3, 1, 4, 7, 2, 9, 8, and then I have 1, 4, 7. What do you think the determinant of this would be? Well, if I use this property here, adding rows or columns, and I use the property that I get zeros everywhere, let's find out. I'm going to go ahead and multiply row 3 by negative 1 and add it to row 1. What do I get? I get 0, 0, 0, 2, 9, 8, 1, 4, and 7. And just as we learned before, the determinant of anything with row of zeros is 0. And I could have done it another way. I could have added a negative of this to this and got a row of zeros on the bottom, and I still could have concluded it will be 0 because we could just switch the rows. But whatever, did it this way. So that's that. That's pretty much all the properties right there that we're getting into. Let's go ahead and actually compute one from example 2. That's really the only they don't give a lot of examples in this section. Example 2 on page 518. Okay. So it says find the determinant of 3, negative 1, 2, negative 2, 4, and negative 3. 4, negative 2, and 5. Okay? Well, we know that this is ugly if we do it the old-fashioned way, but let's try to make our lives easier. Let's notice that if we take, if we take 2 times row 2, I'm sorry, they actually do columns here. So remember, you can add rows or columns together, and we're not quite used to that yet, but so they take 2 times column 2 and they add it to column 3. Okay? So this column, if I multiply everything by 2, that's negative 2 plus 2. Again, I only change the second thing that I write. That rule still applies with the way I do this. So this becomes a 0. And then 2 times 4 is 8, plus negative 3 is 5. And then This is negative 4. When I multiply by 2, add it to 5, I get 1. And then I just copy down everything else. 3, negative 2, 4, negative 1, 4, and negative 2. Alright, let's do another step. Let me multiply column 2 by 3 and add it to column 1. So that's, let's go over here. 3 times negative 1 is 3. Added to this, I get 0. 3 times 4 is 12. Added to this, I get 10. And 3 times negative 2 is 6. Added to 4, I get 2. I'm sorry, negative 6, negative 2. Right? And then I just copy down everything else. Okay? So I basically used this property up here, adding rows and columns. I used it twice. Right? And it's not going to change a determinant, so I don't have to worry about a negative sign or a number in front like some of the other properties. But now, look, I have zeros everywhere, so that's a good thing. So it's just going to be 0 plus this one, negative 1, times negative 1 to the 1 plus 2, times the determinant of this, 10, negative 2, 5, and 1. And then plus 0 if I were to do the other one. So it's really just 10 times 1 minus 5 times negative 2, which is 20. Okay? So just with 2 steps, we made it a little easier. It would have been longer if we did it the cofactor way. All right. So just a couple problems. Let's say they're just trying to get you to identify the theorem here. So number 1, what do? They do 16, 0, 8, and negative 1, and they decide to put an 8 in front, and that's 2, 1, 0, negative 1. So you could say they're using that factoring thing that, remember this, just to say it clearly, the determinant of this matrix, that's what this straight vertical line notation means, once again, is going to be 8 times the determinant of this matrix, which is similar but not the same, because I factored out an 8 here. So all I got to do is write an 8 in front. So now if I were to compute this, it would be negative 16, right? Because the determinant of this is negative 2. Okay, so which is clearly the determinant of this. This is negative 16. I'm sorry for going further than what they asked. Really, they just asked for which theorem did we use. We used theorem 1. Okay, that's what they want. Number 5. They say that 3, negative 2, 0, 0 gives me 0. Well, they're using the fact that any row or column, when you take the determinant, will give you 0. But I mean, with a 2 by 2, it's obvious because you could just do it. You see, you get 3 times 0 plus negative 2 times 0. But now you don't have to do it. You don't have to do the work because you know it's always true. Another big point of math. Okay. That's good. That should get you through the section pretty much. So, good luck.